In this video, I'm going to give a brief overview of bosons as they're understood in the standard model of particle physics. Okay, so again, what are bosons? These are going to include our force-carrying particles. These are particles with integer spin, and what I mean by that is their spin is equal to some integer times Planck's constant h bar, right? So n here can be 0, 1, or 2 times Planck's constant. So that's their spin, which again can be thought of as an intrinsic angular momentum that these particles have. It's not an angular momentum that can be changed. It's an intrinsic value that they have. And one of the important facts about bosons, and one of the things that really distinguishes them from fermions in terms of their behavior, is that we can have multiple bosons in the same state as each other. And that really, really changes the way that they behave. So again, our bosons are primarily made up of our force-carrying particles. So quickly, what are our four fundamental forces that we know of in physics? No, the normal force and friction are not fundamental forces. Instead, the fundamental forces in physics are the gravitational force, the electromagnetic force, the strong force, and the weak force. So all of the other forces that you've learned about in physics courses fundamentally are actually made up of these other forces, right? So friction is not itself a fundamental force. It actually has to do with mostly electromagnetic forces between the atoms, which result in what we observe to be as a force like friction. So these are our four fundamental forces. And you've learned about these. Well, probably not the strong force and the weak force. You'll learn about those in this class, but you've learned a lot about gravity and the electromagnetic force. So you learned about Newton's theory of gravity, and you maybe know some of Maxwell's equations, depending on how far you are in your physics curriculum so far. So it turns out that the way we understand these forces using Newton's laws, this is very non-relativistic. And one way to see that is that signals that these forces seem to send travel at infinite speed, right? If we imagine that we have an electron and a proton, we could calculate the Coulomb attraction between this electron and this proton, right? And, plug it into the equation that you learned in second semester physics. And you could get some value. And now if I move my electron away slightly, that value is going to change. And the way you learn about this in an introductory level course would say that the value, the force that our proton feels when I move my electron, the force the proton feels changes instantaneously, right? When we first learn about electric forces, we have this sort of instant change when we move one of our particles, for instance. And that's bad in terms of relativity, because in a way that's a signal, or not in a way, that is a signal that is moving at infinite speed. So not just faster than the speed of light, that's some instantaneous change. And so that is very non-relativistic. And so this is one of the reasons why we knew that alone couldn't be the full story. And so in particle physics, the way our modern understanding of this is that what happens when you move, for instance, charged particles around, these charged particles, the reason they feel a force at all is because they're constantly exchanging, again, in our electromagnetic case, they're constantly exchanging photons. And so if I move an electron, the proton will know about that because the way they're exchanging photons is going to change. But it takes time for that photons travel at the speed of light. So that signal is going to propagate at the speed of light, but not faster than the speed of light. And so one reason you can understand the need for introducing particles which carry our fundamental forces, which is a really different way of thinking about the fundamental forces. One reason you could think about the need for particles is because then they're going to propagate at whatever speed they propagate at, which cannot be faster than the speed of light. So that's good in terms of relativity. Okay, so now in particle physics, we have particles describing these forces or carrying these forces. So gravity, which is probably the first force that you learned about in physics, would be described by graviton. It's important to note this is actually not currently understood by the standard model. So a graviton would be said to be in beyond the standard model physics because it does not fit into the framework that we currently have, unfortunately, or maybe fortunately, because it gives people like me a job. So the graviton is not in the standard model. The particles that we do understand in the standard model are the photon, which carries the force, the electromagnetic force, and we usually use the Greek letter gamma to represent our photon. The strong force, and the particle associated with the strong is the gluon. We usually use a lowercase g for that. And then the particles associated with the weak force, there's actually 3 of them. There's the Z boson and the W plus or minus boson. And maybe it's nice. These don't have any other fancier names that I'm just not telling you. Literally, it's just the Z boson and then the W plus and minus bosons. There are 3 of them, and we just call them by their letters, and then we use those letters, usually a capital form of those letters, to represent them. And so if we go to our chart of the standard model, we can see these particles appearing, our gluon, photon, Z boson, and then that W boson comes in a plus and a minus. So those are most of our bosons. There's one more boson, which is the Higgs boson. It is our most recently discovered particle. It was just discovered in 2012. This boson's a little different. So it's the only one in the standard model that has 0 spin. It's a scalar particle. It doesn't have any spin. And the Higgs field, so the Higgs particle is an excitation of the Higgs field. This is what we'll learn in this class, that particles are excitations of fields. The Higgs particle is an excitation of the Higgs field. The Higgs field is responsible for why massive particles have the mass that they do. It has to do with the interaction with the Higgs field. So a lot of people will loosely say the Higgs particle gives other particles mass, and particle physicists often hate that because that's not really the right way to think about it. The Higgs particle is an excitation of the Higgs field, and the Higgs field gives particles mass. That is a topic for very, very far in the future, but an important one, but an advanced one. So we'll get there eventually. All right, so those are our bosons that we know of and that are described in the standard model of particle physics.